Hi there, we're going to work out the maths behind elastic collisions in one dimension. So we have object 1 with initial velocity u1, object 2 with mass 2 and initial velocity u2. If they collide, they'll be momentarily joined. They might deform during that time, but after that time they will fly away in their own directions with velocity v1 and v2. Of course, the masses m1 and m2 will remain unchanged. An elastic collision is perfectly springy, so none of the kinetic energy is lost as heat or sound or squishing up in deformation or anything like that. One way of recording this would be to say that the sum of the kinetic energies beforehand, the sum of half mu squared, would be equal to the sum of the kinetic energies afterwards, which would be half mv squared. To do this from first principles, the maths gets really messy. Thankfully, there is a shortcut. For two particles with an elastic collision, we have particle 1, particle 2, the initial velocity plus the final velocity of particle 1 is equal to the initial velocity plus the final velocity of particle 2. Praise the Lord. We still need the conservation of momentum. So first mass times its initial velocity plus the second mass times its initial velocity is equal to the first mass times its final velocity plus the second mass times its final velocity. We have particle 1, 6 kilograms, colliding with particle 2, which is 10 kilograms, and you can see the initial velocities there. So you can see m1 is 6, u1 is 4, m2 is 10, u2 is negative 2 because I've assigned left to right, the rightwards direction as positive. If I substitute into the shortcut formula, we see 4 plus v1 is equal to negative 2 plus v2. I'm going to look at the positives and negatives and see how I can keep things as simple as possible and get an expression for one of those variables. So I can add 2 to both sides of the equation, and I get v2 is equal to 6 plus v1. So I'm going to use that instead of that. Now if we look at the conservation of momentum, we see the momentum before equals the momentum after. We substitute in all the numbers that we know, we get that. But wait a minute. We have two variables, v1, v2, so we can't solve the equation, but look at this. Remember, we have an expression for v2, so we will substitute 6 plus v1 instead of v2. When we put that in and expand the brackets, that's what we get. So we get minus 56 is equal to 16 v1. We swap sides and we're left with v1 is negative 3.5, in other words, a velocity of 3.5 meters per second to the left. Now we have that earlier equation that v2 is equal to 6 plus v1. So we see that v2 is 2.5. So if these two particles collide with those velocities before the collision, and then after the collision they bounce back with those velocities shown, and that's how you do it.